An instrument landing system is a radio navigation aid used by aircraft during the approach and landing phases of a flight. This system plays a crucial role in low visibility conditions, allowing pilots to execute precision approaches and landings even when visibility is limited due to factors such as fog or poor weather conditions. ILS is widely employed at airports around the world to enhance the safety and efficiency of aircraft landings. One of the two main components is the localizer, which is specifically designed to ensure lateral alignment. By transmitting radio signals, the localizer provides crucial guidance to pilots, facilitating precise alignment with the runway centerline. The localizer is displayed with the logarithmic periodic antennas here. Those are broadband antennas consisting of a number of dipole antennas whose length and spacing decrease towards the direction of radiation. The row of antennas is located around 300 meters behind the threshold of the opposite landing direction. The localizer antenna emits two lobes. The left one is dominated by a frequency of 150 Hz, and the right one is dominated by a frequency of 90 Hz. Based on this modulation, the position of the aircraft can be determined by the DDM, the difference in depth of modulation, by the dominant frequency in space. If the aircraft is flying optimally, the power of both lobes is received in equal parts. The DDM is therefore equal to 0. If, on the other hand, the aircraft is flying too far to the left of the runway, larger portions of the lobe, where 90 Hz is the dominant frequency, are received. This results in a DDM greater than 0, and a fly right indication is displayed to the pilot. If the aircraft flies too far to the right of the runway, 150 Hz is the dominant frequency, and the DDM is less than 0. The pilot now receives a fly left indication on the display. A 90 Hz and a 150 Hz signal are each modulated by conventional AM onto a carrier frequency of 109.5 MHz. Both of these signals are inputs for a hybrid ring splitter. A hybrid ring splitter has two inputs and two outputs. For the first output, each signal takes a quarter wavelength to reach it, thus adding up in phase to each other. This is displayed by the sigma sign. For the second output, one input again takes a quarter wavelength, while the other needs 3/4 wavelengths to reach the output. That way, the input signals are added up with a 180-degree phase difference and therefore can be seen as a subtraction, which is displayed by the delta sign. The inputs do not interfere with each other because they always cancel themselves out at the other input. This is because they reach it with a 180-degree phase difference to their own signal. One of these hybrid ring splitters is used to create the CSB and SBO signal. The previously modulated 90 and 150 Hz signals are the inputs for the splitter and thus add up at the sigma output, resulting in the creation of the CSB signal, which contains the carrier and equal sidebands. At the delta output, they are subtracted from each other, cancelling out the carrier, resulting in the SBO signal, which contains equal sidebands with the 90 Hz signal in antiphase to the 150 Hz signal. Next up, both the CSB and the SBO signal are inputs for another hybrid ring splitter, with the SBO signal being 180-degree phase shifted to achieve the desired output at the antennas. The sigma output feeds the antennas above the centerline, adding up the CSB and SBO signals in phase, which results in a predominant 150 Hz tone. The delta output feeds the antennas below the centerline, adding up the CSB and SBO signals in antiphase, which results in a predominant 90 Hz tone. Since the SBO signal is added with a 180-degree phase difference between the antennas above the center line and the ones below, the signal cancels itself out on the center line. That way, only the CSB signal is present on the center line and no tone is predominant. The space modulation of the signal can furthermore be influenced by the number of antennas. If the number of antennas increases, the lobes of the CSB and SBO signals become narrower. That way, the signal is more precise towards the center line. The CSB and SBO signals transmitted by the localizer produce a space-modulated signal. When demodulated, the modulation depths of the 90 Hz and 150 Hz signals are dependent on the position of the aircraft. The difference of these two depths, therefore, gives the aircraft information about its position. When the aircraft is located to the right of the optimal approaching angle, in the area where the 150 Hz signal is predominant, the DDM is smaller than 0. As shown in the spectrum, the 150 Hz is of higher proportion than the 90 Hz signal. The pilot now gets a fly left signal that guides him back onto optimal alignment. When the difference is 0, the aircraft is on the optimal route because both frequencies have the same modulation depth. When the aircraft is located to the left of the optimal approaching angle, in the area where the 90 Hz signal is predominant, the DDM is greater than 0. The pilot now gets a fly right signal that guides him back onto optimal alignment. The sum of the depth of modulation is the 90 Hz part and the 150 Hz part of the signal added together. The SDM always stays the same since when the 90 Hz signal increases, the 150 Hz signal decreases and vice versa. For the localizer, the SDM is always at 40%. Due to the different modulation methods, the CSB and SBO lobes have the presented form and are modulated onto a single carrier. This causes problems because buildings, cars, and other objects can create reflections of the localizer beam, which might interfere with the signal on the center line and cause an approaching plane to receive a fly-right signal when it shouldn't. To avoid reflections, the localizer beam can be narrowed by using more antennas. This, however, also increases the side lobes each antenna creates, which could end up as a misleading course signal. Furthermore, ICAO has guidelines that need to be fulfilled. The localizer beam has to be in an envelope of plus/minus 10 degrees at a distance of 25 nautical miles. Furthermore, at a distance of 17 nautical miles, the aircraft needs to receive a signal at plus/minus 35 degrees. This would not be accomplished with the current system. That is why another carrier is used, where the same audio signals are modulated on, but with less power on the center line. This signal is only fed to a couple of antennas, thus creating a broader beam. This beam is labeled clearance signal, while the more powerful narrow beam is named course signal. The carrier frequencies of both signals are 8 kHz apart from each other. In this example, the ILS channel frequency is 109.5 MHz. The course signal is 4 kHz above the channel frequency, while the clearance signal is 4 kHz below. If the airplane's position deviates from the center line, the received power from the signals reduces, while the course declines stronger than the clearance signal. The closer the aircraft gets to the center line, the greater is the power it receives from both signals, with the course signal being a lot stronger than the clearance. Due to the different power levels of the course and clearance system around the center line, the aircraft receiver only picks up the less disturbed course signal, while the reflections of the clearance signal will now be suppressed by the course system on the center line. The optimal landing approach leads through the two lobes of 90 and 150 Hz in a straight line to the runway, where the DDM equals 0. Now an optimal landing of an aircraft with the localizer is shown. The receiver of the localizer signal is located at the nose of the aircraft. The aircraft now approaches the runway in a straight line. The glide path constitutes the second key component of the ILS. Tailored for vertical guidance, the glide path assists pilots during the approach and landing phases. It enables precise descent along a predetermined angle, ensuring the aircraft maintains the correct flight path for a safe and accurate landing. The glide path antenna is located 150 meters next to the center line at the level of the aiming point of the approaching aircraft. This is 300 meters from the beginning of the runway. The glide path antenna transmits a 90 Hz dominant signal and a 150 Hz dominant signal. The glide path signal is modulated onto a carrier frequency between 329 MHz and 335 MHz. This frequency is always coupled with the localizer frequency. In this video, the frequency pair with a glide path frequency of 332.8 MHz is used. Here too, the space modulation produces a lobe at a dominant frequency of 90 Hz and a lobe at a dominant frequency of 150 Hz. The operational range to receive a usable signal from the two lobes is 10 nautical miles. Viewed from the side, the lobe dominated by 90 Hz is positioned higher than the lobe dominated by 150 Hz. The optimum glide path, which usually has an angle of theta equal 3.0 degrees, is located in the middle of the two lobes. A usable signal is received when the aircraft is at an elevation angle of 0.9 degrees to 5.25 degrees with a 3.0 degree ILS to the runway. The receiving antenna for the glide path signal is located on the nose of the aircraft. In an optimal approach, the aircraft flies between both lobes where the DDM is equal to 0. The signal generation for the glide path works like the localizer one. A 90 Hz tone is once added in phase to a 150 Hz tone and once in antiphase. In case of the glide path, the message signals are modulated onto a carrier frequency of 332.8 MHz. The CSB signal is created with conventional AM and a modulation depth of 40%, while the SBO signal is modulated with a suppressed carrier. Taken both signals independently, the power of the 90 Hz and 150 Hz tones are the same, but when added or subtracted from each other, that changes due to the different phase. Adding both signals up results in a predominant 90 Hz tone, and subtracting the SBO from the CSB signal results in a predominant 150 Hz tone. The DDM and SDM for the glide path work in the same way as for the localizer. When the aircraft is located above the optimal approaching angle of 3 degrees, the 90 Hz signal is predominant. The spectrum on the right shows the carrier in red and the 90 Hz and 150 Hz parts in green and blue. The part of the 90 Hz signal is now higher. This results in the DDM being greater than 0. The pilot now gets a fly-down signal that guides him back onto the optimal glide slope. When the difference is 0, the aircraft is on the optimal route because both frequencies have the same modulation depth as displayed in the spectrum. When the aircraft is located below the optimal approaching angle, the 150 Hz signal is predominant. The spectrum on the right shows that the 150 Hz part of the signal is greater than the 90 Hz part. This results in the DDM being smaller than 0. The pilot now gets a fly-up signal that guides him back onto the optimal glide slope. For the glide path, the SDM is always at 80%. So far, only the null reference glide path has been looked at. It has 2 antennas, and the lobes of the CSB and SBO signals are symmetrical to the common angle of 3 degrees. Due to their symmetry, the signals have a relatively high level even close to the ground. As a result, buildings or elevations can cause reflections that distort the glide path signal. There is another type of glide path, the M-type glide path, that solves this problem with its adapted beam pattern. To weaken reflections from obstacles close to the ground, the lower part of the glide path signal is decreased and the upper part is increased. It is important to decrease and increase the CSB and SBO signal in the same way to still ensure correct DDM proportions. An approaching aircraft receives the same fly-up or fly-down signals as it would approaching on a null reference glide path. Since the glide path signal is decreased close to the ground, the signal coverage gets narrower, the closer an approaching aircraft gets to the runway. To ensure a wide enough coverage, even close to the runway, a clearance signal is needed. The clearance signal for the M-type glide path is basically a fly-up signal. Because of antenna beam patterns, there is a clearance signal below and above the glide slope, but due to the capture effect, only the clearance signal below the glide slope is being used to send aircrafts back onto the optimal glide slope. To achieve these specific beam patterns, the glide path now needs 3 instead of 2 antennas. To understand how the lobes of the M-type glide path are created, it is important to first know the pattern of each individual glide path antenna. The null reference glide path has 2 antennas. The lowest antenna, at about 4 meters height, radiates the widest pattern, shown in red. The other antenna, at about 8 meters height, radiates the pattern, shown in orange. The M-type glide path has an additional antenna at about 12 meters height. It radiates the narrowest lobes. The lobes are alternately in phase and anti-phase to each other, which is shown here as plus and minus. These individual lobes can now be overlaid to create the CSB, SBO, and clearance lobes for the M-type glide path as shown in the following. To create the radiation pattern needed for the CSB signal, the signal is radiated by the lowest and middle antenna. The 2 patterns overlay to create the CSB lobe of the M-type glide path. Since the antenna pattern consists of lobes that are alternately in phase and in antiphase to each other, the level of the upper part of the overlapping lobes is added and the level of the lower part is subtracted. In this way, the CSB signal is amplified towards the top and attenuated below 3 degrees. To create the radiation pattern needed for the SBO signal, all 3 antennas are used. How they overlay to create the SBO lobe of the M-type glide path is shown in the following. The radiation pattern of the middle antenna is the base of the SBO signal. It creates the same lobes as the null reference glide path would have. The pattern of the lowest antenna, A1, is now added to increase the positive upper part and to decrease the level of the negative lower part. To make sure that the 0 point is still at the correct angle of 3 degrees, the pattern of the highest antenna, A3, is added to even out the shift that was caused by antenna A1. To achieve a radiation pattern suitable for the clearance signal of the M-type glide path, only antenna A1 and A3 are being used. They send out a fly-up signal that is a 150 Hz dominated signal to get aircrafts flying below the 3-degree angle back onto the optimal route. The clearance signal needs to cover a wide enough area below the angle of 3 degrees to compensate for the attenuation of the course signal in that area. It should also be as low as possible in the area around 3 degrees to make sure that the course signal in that area is stronger than the clearance signal. To achieve this, the lobes of antenna A1 and antenna A3 are added. They level out to 0 at the angle of 3 degrees and add up below 3 degrees. Therefore, a coverage for the intended area is achieved. The interference of the patterns of antennas A1 and A3 also creates a high-level signal above 3 degrees. Due to the capture effect and the much higher course signal in that area, this signal, however, is not relevant. The CSB, the SBO, and the clearance signal together create the M-type glide path as it is shown here. It has the same function as the null reference glide path, but interference from objects on the ground is significantly reduced. As was shown before, above the lobes which result in the 3-degree glide slope, there are further lobes with the same attributes. These lobes lead to an undesirable secondary glide slope at an angle of 9 degrees. An approaching airplane, as shown, would capture the 9-degree glide slope instead of the desired 3-degree one. This can be very dangerous since the onboard equipment of the airplane doesn't recognize the difference between the correct and the false glide slope. If the aircraft continues the approach on the 9-degree glide slope, the landing would be too abrupt, which could result in an unsafe landing or even a crash. To prevent this case, the approaching airplane needs to be in a specified area, which is set by ICAO. Another important component for this system are markers. The outer marker, the middle marker, and the inner marker. There are 3 markers that are part of the ILS: the outer marker, the middle marker, and the inner marker. Inner markers are very rarely used nowadays. The markers are each at a defined distance to the runway and help the pilot know his exact position during the approach. Since the approach angle should be about 3 degrees, the pilot not only knows the aircraft's distance to the runway, but also what its approximate height should be when receiving the marker signal. As can be clearly seen, the distances of the markers to each other get smaller the closer they are to the runway. The middle marker is about 0.5 nautical miles away from the runway, whereas the inner marker is only 1,000 feet away from the runway. Overall, the markers help the pilot stay on his optimal approach route. The marker receiver is on the bottom side of the aircraft. The acoustic signal broadcast by a marker is played out loud in the cockpit to signalize the pilot that he is passing a marker. The outer marker is identified by a 400 Hz tone, which is audible in the cockpit in a dash-dash pattern. The middle marker is modulated with a 1300 Hz tone, heard in the cockpit as a dash-dot pattern. Lastly, the inner marker is modulated with a higher frequency using a 3000 Hz tone, producing a dot-dot pattern in the cockpit. How this sounds in the cockpit will be demonstrated shortly. The audio signals broadcasted by the markers have different frequencies. The inner marker is a 3000 Hz tone, the middle marker a 1300 Hz tone, and the outer marker a 400 Hz tone. These signals are then modulated onto the carrier frequency of 75 MHz. This is done with conventional AM using a modulation depth of 95%. The markers can be replaced by a component called DME, which stands for Distance Measuring Equipment. The pilot can use the Distance Measuring Equipment System, abbreviated as DME, to measure distances during the landing approach. These navigational aids can be used for navigation during all phases of the flight. In the context of ILS, it is used to measure the distance to the touchdown zone of the runway. These ILS DME are called collocated DME. Its antennas are located at the glide path mast. There is a distinction between collocated and aerodrome DME. The latter is presented here. In this case, it is used at the airport for an ILS. This is a special use of the DME. When using a collocated DME for an ILS, this can replace a marker. The DME interrogator of the aircraft is located at the shown point. The minimal distance a DME has to be interrogated for ILS coverage is 25 nautical miles. The DME works in a range of frequencies between 962 and 1,213 MHz. To determine the slant distance between DME and aircraft, the aircraft is sending a specified double pulse at time T0, which is received by the ground station at the time T1. The time between receiving and sending back the double pulse is exactly 50 microseconds. The time the aircraft receives the pulse is called T2 in this context. The aircraft is moving as well, but in contrast to the double pulse, which is moving with speed of light, it can be neglected. Using the time difference, the slant distance ρ between DME and aircraft can be calculated with the shown formula. Simulating that the displayed aircraft could move up and down on the spot, we want to look after what happens if it deflects from the ideal ILS guidance. That's why the instruments show an ascending flight, even if a pilot would just decrease the descent rate. The higher the aircraft flies above the ideal glide path, the greater the deflection on the scale next to the altitude display in the primary flight display, PFD, displayed top left. The horizontal situation indicator, HSI, displayed top right, displays this next to the course instrument. Once beneath ideal glide path, both pointers swing in the other direction, true to the saying, always fly to the needle. Flying left leads to a deflection of the marker in the PFD beneath the artificial horizon, and simultaneously the deviation bar of the HSI moves to the right. Getting right of the ideal localizer beam, both indicators move to the left. The following illustrates how it sounds in the cockpit. The airplane first passes the outer marker. It only serves as a pre-entry sign. The middle marker then has a faster pattern with a higher frequency and sounds as follows. The inner marker then sounds like this. Thanks to all these components of the instrument landing system, a safe landing is guaranteed.